Alright, so check this out. Here's what we got. We got ourselves some dude hanging off of this slope right here. And let's kind of put a little tether right there. And let's make the dude a block. Okay? And the block has a mass m, right? And it goes off at an angle theta. This is a terrible marker. But I even have this in my pocket. There we go. Is that better?
Yeah.
Alright, I like that better. Alright, so we got a mass m. The block is at an angle theta. Figure out the tension that is in the rope. T. Put a little arrow going up there. That's a T. Alright. What I would do is, first thing I would do is I would have to shift my coordinate system. So I've got X and Y. We cool with that?
Yeah.
Basically, you took your coordinate system and you turn your head this way a little bit. Then what I'm going to do is I'm going to take this guy and I'm going to break him up into its components. So I've got the normal force here. I've got the angle, or I've got the W here. That W is going straight down, but since my coordinate system is shifted, then this W is now at an angle, and the angle here is theta. Did I lose you on anything?
Nope.
Okay, so I'm breaking that up into its components. This is W, this is W X, and this is WY. Wx is W sine theta. Sorry, W sine theta. Wy is W cosine theta. You cool? Happy, happy? Awesome. Alright, let's add up the forces. Is there any other forces? I guess that's a good question to ask. And the answer is, since we're talking about somebody sliding down the ice, the whole point of the story of ice is so that you can kind of assume that there's no friction involved here. So I don't need to add in some kind of frictional force, either going that way or that way. So let's add up the forces in the x direction. Is the person accelerating in the x direction?
Yes.
No.
No, no acceleration, but
Right, you better hope he's not accelerating down that icy slope, right? Or else he's going to die. So he's not accelerating, zero acceleration. So adding up all the forces, I've got Wx, and that's negative Wx because it's going down and my positive direction is up that way. And I've got positive tension is equal to 0. So tension is equal to W sine theta. Are we cool?
Yeah.
Alright. That's my answer. If I were to check the units, now what I'm going to do is I'm going to talk about, like, well, what is it that we can do to kind of mess with this thing? Not mess with it, but check to see if we're spot on. The units for W is in newtons. It's a force, right? The units for sine of theta, that is unitless, so it has no units. So I'm saying that tension is going to be measured in newtons, which is good because tension is a force to begin with. So the units work out, right? Now what I'm going to do is I'm going to run myself through a few checks, and this is kind of what I also like to do. I like to kind of think about, well, what if this gets really big or if this gets really small and all of that kind of stuff. Now, the only thing that I see here is the W. By the way, W is the same as mg. Because I realized they gave us the mass, but they didn't give us the weight. Did they give us the weight or the mass? Oh, they just said mass m, so they gave us the mass. All right, so this is actually my answer. But if the mass increases, what happens to the tension?
it increases.
Right. I mean, if you look at this, it's in the numerator, obviously, and if that gets bigger, then the tension also gets bigger, so we're good. And if gravity increases, it also gets bigger. That's kind of trivial, but the real question is, well, what happens when the angle starts getting messed with? What happens when I start changing the angle of this thing? And now that one I can kind of think about like this. The angle theta Do you remember, do you know what the sine of 0 degrees is?
I think it's 0.
Yep, perfect. And do you know what the sine of 90 degrees is?
1.
Yeah, that's exactly it. All right, and then there's all the ones in between. But usually when I try to vary my angles, when I try to change my angles, see if it's bigger or smaller and how that affects the graph. What I like doing is I like thinking about, well, what's 0 and 90 when I talk about angles. Okay, if I plug in 0 degrees into here, what is my tension going to be? Looking at it mathematically, looking at this equation mathematically. If I plug in,
It's the same as your mass and gravity.
no. If I plug in 0 for theta, that would make sine of 0 0. What's 0 times mg?
0.
Perfect. But does that make sense to you?
Yeah.
Because if I brought this incline down to 0 degrees, then the question is really asking, what's the tension in that rope? It's nothing. There is no tension in that rope. Right?
Right.
It's kind of a dumb question. All right. What about theta equals 90 degrees? What would happen? If theta equals 90 degrees, what would happen to sine of 90?
It would turn into 1, so tension would be equal to mass times gravity, or weight.
Right? It would equal to the weight, which also makes sense to me, right? Does that make sense to you?
Yeah.
Because, if you think about it, like, if you got a 90-degree thing, then basically you're saying, it's kind of like, say that there's a rope on this wall and I'm hanging off this wall and I'm just touching the wall and I ask myself, what is the tension felt in the rope? Well, it's going to be the weight that I'm pulling at it because the wall doesn't make a difference. I could come off that wall and it would still have the same amount of tension. Does that make sense?
Right.
So
Yeah.
turning this over to 90 degrees negates the fact that it's touching the ground, and then turning this over to 0 degrees means all of that weight is going into the ground, and all of that, the ground is pushing directly up on it, so there's no tension going right or left. Does that make sense?
Yeah.
Well, that's it. That's the whole problem right there.
Cool.